Welcome back. Today I want to study images from some of the other parts of the spectrum. We've already studied images from the computational side. What would it take to make a data structure that captures the concept of the actual outputs of a function? Today I want to explore the other two extremes. What does it look like for a scientist to reason about the images in some intellectual sense? And what does it look like in real life with actual data? Let's start with the actual data and then retreat to the middle. Imagine we're asking for the image of the clients that come to our store. I'll remind you of the story. We have a filing system to store the information about our clients. When we plan for this, we should assume that anyone could be a future client. We therefore make forms that allow us to enter data for an arbitrary visitor. Any phone number could exist. However, when it comes to calling our clients, we should only actually call phone numbers that exist in our database. We can see the dilemma. We have to create a codomain, that is, a place for outputs, that is robust enough to take in any future possible phone number, but won't actually have the phone numbers. The interest in the image is to keep track of the fact that the phone numbers that we actually do receive are just some smaller part of the larger filing system. This is the key concept between images of a function and the codomain. The images are generally not the entire output set. Now, when we engineer a data type to control this, we focused on the issues of how to make that data transferable. Now let's ask the realistic question of what do we even mean by the image of our client list? Notice that seems to depend on time. Our clients will change over time. Hopefully, we keep adding new clients, but on occasion we may even lose clients. The result is that we can't actually even discuss the concept of the image of a function without including some type of modalities. That is, we have to think of the concept of being a member of our client list as depending on which possible world we're in, and that can change. We saw in our previous videos with dealing with modal logic, we have to introduce something called a state machine or a possible worlds graph. So how do we pass these modalities along to our actual user? This could appear in your browser as a simple toggle switch. What's hiding behind there is a state machine. Let's assume that the green setting is that a good website must pass the filter. What we'd say in modal logic is that it's necessary that the chi test is false. Remember, our chi test is deciding whether a website is on the naughty list. So we should be false if we're going to pass the filter. This test might be too aggressive. It might send too many warnings to the user, and at some point they may wish to turn it off. By selecting the red mode, they transition to a new state. Here, known bad websites may now pass our testing because we've disabled some of it. In this case, we would change to the diamond, meaning it's possible that chi of A equals false. We wouldn't know for sure. At this point, we can see that we're drawing a picture that changes what subsets we think of as the websites we can browse without a warning. It is said that I'm changing the state of the state machine. I think of myself as living like a player on a board game that moves between squares, based on what they roll, the selections they make. The range of possible modalities is quite vast, so let's narrow it to the concept of a temporal modality. Typically, when we think of a temporal mode, we think of something that can be advanced. However, there are still some choices in there. We could think of something discrete. For example, we might only talk about which clients we have in a particular month, say January. Then we could see that that could change every year, so it could be periodic. We could always return to the January numbers, return to the February numbers, the March numbers, and so forth. That would be one version of a temporal modality. We could be more specific. We could look at January in 2024 versus 2025 and keep upgrading the year. In that point, it would be something that doesn't repeat. It's aperiodic, and it continues on into the future. That would be another possible world that would also be in the temporal sphere. You can even get into discussions about whether it's discrete or continuous. That is, are we looking at things that happen on one day, then the next day, then the next day? Or do we get into the hours, minutes, seconds, and milliseconds between events? Since time can be divided up as much as we want, in principle, we have the opportunity to use an entire line for time if we like. The key takeaway is that the concept itself of the image of a function is dependent on these possible worlds. You can't simply describe the image of a function in this particular context. Here's how we can summarize the effect of a temporal logic. Our state machine either continues in one direction in time as an infinite sequence, or it might loop back on itself. This would be a periodic time zone. We can also further think of these as discrete steps that go at specific intervals in time, such as each day or each hour, or they might be continuous. We can always subdivide and add points in between. At this point, once we've settled the state machine, we can return to a classical view of what it means to have an image. That is, we're taking into account that we are in one specific world at a time. At that point, there's no more ambiguity about the image. There's a specific set of clients at that specific point in time. And notice what's left to decide. We don't care about the technical details of how to store an image. We've already handled that with our computational data type for images. And we also no longer care about what state, what possible world we're in, because we're assuming we fixed that as well. So what we're left with is to worry about what a classical scientist would mean by an image, a frozen in time unit that we can describe precisely as being true or false. So let's clear the board and write down what a classical image should look like. So setting aside issues of computation and issues about the modality of the real world, we're now left with a specific, concrete classical question. This is when we can turn away from data types and start talking about sets. Sets, I'll remind you, are just data types that have a particular restriction. We only choose to study them through their membership, which we write with a little e, saying X is a member of or an element of A. Since we're only able to ask for whether something is in or out of a set, it simplifies a lot of our logic, and it lets us talk about things like subsets. We say that C is a subset of B if every element in C is an element of B. Try to think about the element of as an abstract test for true and false. It doesn't have to mean membership in any physical sense. So while it's sometimes helpful to think of a set as a bag full of marbles, the marbles are the members, or to think of a list of numbers and the elements in the list are the members, those each introduce physical realities. For example, a list comes in some order. Marbles might be repeated. These are not properties that a set would even notice. The set simply has to judge, am I a member or not a member? The more you divorce yourself from examples and think of this just as a Boolean test, the more you're getting onto what a real set means. With that model in mind, whatever C and B actually are as substances no longer matters. We're simply saying that whenever U passes the membership test for C, then it also passes the membership test for B. Notice what we've done then is we've created a larger test, the subset test, based on repeating smaller tests, the membership test. What I'm going to try to do is take the knowledge that C is a subset of B and encode that with a function. The function itself will not be new. It'll simply be the identity function. However, what I will do with this identity function is that I will choose to introduce it with a very specific type, a type that keeps track of my sets C and B. Remember that in order to give a type to a function, we had to prove that whenever the input had the type of the domain, the output had the type of the codomain. The constructor for a function has to take in something like a program, which I've written as phi. The next thing is I have a variable. The variable here is simply to tell me what I'm going to substitute. We have some rules to substitution. The good news is the computer knows those rules and it will execute them. The proof line is us telling ourselves that we better be certain that if we were giving it data of type A and replacing our string everywhere that had the variable x with A, that would produce B. Once we have it, then the assignment of x to the variable for phi will have type A to B. So what type am I going to give as an input? I notice here that whenever U passes the membership test for C, it will also pass the membership test for B. So suppose that I choose to think of C and B as data types described purely by this membership test, meaning you get to introduce values of type C if the membership test passes. Given that interpretation, for data to have type C is for data to be an element of C. If that's the case, then it's also automatically an element for B. As a result, we are allowed to introduce this function as having the type C to B. But there's more we can do. Since our function is actually just the identity function, it naturally has a left inverse. Just send x back to x. Since this function has a left inverse, that means that we can look back at the original function C to B and ask that it be injective. One of the equivalent ways for injective to exist is if there is a left inverse. Remember, however, that left inverses are only partial functions. That is, for every B, it maybe gives me something of type C. This is acknowledging the fact that not every member of B has to be a member of C. Whenever we have a function with a partial function left inverse, we call that injective and we give it the hook symbol. What we've now done is engineer from the subset condition, which is just a true-false rule, a function which we think of as the inclusion function. It makes no sense to talk about an inclusion function just on the level of the program, that is, the lambda calculus. It only makes sense to describe it using its type. It's the type that encodes the C and the B. the subset relationship that we're trying to discover as a function.
The right inverse of the inclusion function is known as the membership test.
So let's repeat what we've said. We started with a subset and we created an injective function from C to B. But the reverse is also true. If we start with an injective function, we can produce a new type of set. The set we get is called the classical image. So here's what I want to manufacture. I start with a function f from a to b, where a and b are sets. And I'd like to create a function which describes just the actual outputs, the values f of a, as we range over all the things that will be members of big A. To make this precise then, we need to give it an actual set we can build. We can think of the bottom set as defining what the top set means, but it turns out there's a nuance in the mathematics. We've seen that there are many functions that are defined without a domain and codomain. When that happens, we might feed as inputs values from a set A, but we struggle to know what B should be. It doesn't exist yet because we haven't created it. In fact, we want to match that set with whatever does come out of that function. So this top line has to be a set all on its own. The logic of set theory is to allow both ways of constructing a set to be valid ways to form the image, and it's set up so that whatever the two answers give is declared as identical. Identical just means that when we test membership, they come back the same. Ignoring the technicalities, we notice that this bottom one is clearly a subset of B. Why? Because we're starting out with values which are definitely members of B, and we're restricting them by some condition. Therefore, anything that's a member of this is already a member of the larger set B. In this way, what we've done is we've taken a function and produced for ourselves a subset, which is known as the classical image subset. It is often abbreviated IM of F. Since we can take subsets and produce functions, and we can take functions and produce subsets, it'd be nice to understand what happens if we apply this process repeatedly. For example, we could begin with a subset and create a function. Then using that function, create a new subset. We'd like to know if this new subset has any new information. And the answer is it does not. Whatever function we got from here, once we create the subset, will already be the subset we started with. But wait, there's more. Whatever function we start with, we can create the image of that function, and then use that to create a new function. Now here's something really does happen. We see that we trade an arbitrary function, f from a to b, for one that is injective. This is precisely the injective function we saw in our computational description of image functions. It's the part that lets us write that universal property. The filing function, therefore, must be injective. One client, one folder. That is, f of x equals b has at most one solution. The use of images guarantees that the useful properties of injective functions are available to your program, but without having to start with an injective function at the beginning. Taken together, we now see what's known as a resonance theorem. This is something that when you apply it the first time, it may change your data. But if you apply it repeatedly, you get back to where you started. You're in a loop. You resonate. We can either start with a function, take its set theoretic image, and convert that into an injection, or we could start with a subset and convert that into a function. However we do this, we end up with the same sets. Therefore, images are one of the main ways that we create subsets. We create a function on a set that we've never explored before, and it limits us to just some parts of that set, these image subsets. And likewise, if we have a subset, we're guaranteed to have a function to go with it. It just happens to already be injective. Taken together, we see the bridge work. The injective function is what we need when we need to go down to a program and describe the data structure to compute the images. But once we need to reason about it and work in terms of models, we would do better to invite this classical set theory model of a subset of this codomain. Each of those could then in turn be refined based on modalities. For example, at what time of day did the client list get printed? This will change what exactly membership means. But we can still back up at any fixed point in time the membership as a classical set concept. In a classical story problem, you may find that you need to use all three of these types of thinking about images, both computational, the classical fixed value, or what it means in a specific modality. Being conversant in the differences and their similarities will make you a powerful programmer. Until next time. That's how you take care of your chalkboard.